Very good evening, students.
Good evening, sir.
Good evening, sir.
Good evening. So last class we were discussing about Cannizzaro reaction, and this was a mechanistic approach which we have discussed. So aldehyde, which is most reactive towards nucleophile, that is OH minus, will be oxidized because in the first step the OH minus is attacking the electrophilic carbon, and the rate determining step is transfer of hydride ion. That is, hydride ion is acting as a nucleophile to attack the second molecule of respective carbonyl compound, which is not having any alpha hydrogen. And ketone do not give the Cannizzaro due to poor leaving tendency. So look at the examples. What are the products obtained here? Benzaldehyde treated with a constant NaOH upon heating. So self oxidation and self reduction. So you'll get carboxylate, sodium benzoate you will get. Along with that, you will generate the alcohol respect to benzyl alcohol. Self oxidation C double bond O minus Na plus, and self reduction. That means carbonyl compound will be converted to respect to carboxylic acids or carboxylates and alcohols, and that is happening in the Cannizzaro reaction. And which carbonyl compounds? The aldehydes will undergo which do not have alpha hydrogen. Look at this reaction, cross Cannizzaro reaction. When Cannizzaro reaction is carried out between two different reactants, which will be oxidized, students?
Formaldehyde.
The oxidized, which substance is going to be oxidized? That substance which has greater reactivity towards the nucleophile, that will be oxidized. Here when you look at the benzaldehyde and formaldehyde, formaldehyde is more reactive towards OH minus, so that will be oxidized. So we'll generate HC double bond O minus Na plus and C6H5 CH2OH. These are the two components which are going to be obtained. C6H5 CH2OH and HC double bond O minus Na plus are going to be obtained. Intramolecular Cannizzaro reaction, that means in the same species oxidation as well as reduction is going to happen. So HC double bond O, C double bond H. If you look at the mechanistic approach, HC double bond O, C double bond H attacked by OH minus. OH minus acts as a nucleophile, attacks this particular carbon. Pi electron density moves away. You generate HC double bond O, CO minus CH, COH. Negative charge and oxygen comes into hydride ion lost. Loss of hydride ion. You generate HC double bond O, C double bond OH, and the hydride ion which is lost in the previous step, that acts as a nucleophile, attacks the electrophilic carbon. C double bond pi electron density moves away. You generate HCO minus, C double bond COH, and O minus will try to pick up the proton, forming H. Here also we have CH bond. Here we have COH, CH, C double bond O minus. So this is going to be the product form. CH2OH, C double bond O minus, and that will have electrostatic force of attraction with Na plus. C double bond O minus Na plus CH2OH. That is going to be the correct set of reagents. That is the correct set of product obtained. C6H5CHO, again C6H5, C6H4NO2CHO, concentrated NaOH. So we have two CHO groups. So which is going to be oxidized and which is going to be reduced, and why? I'll give this as A, this as B. So which carbon is going to be getting oxidized? That carbon which is more reactive towards the OH minus, that will be oxidized. Which is more reactive towards the OH minus, nucleophilic addition?
Sir, B.
Why, Nandana?
Just because NO2 is a withdrawing group, so C will be
Yes.
more positive.
Yes, very good. NO2 is a very good electron withdrawing group. It withdraws the electron density by mesomeric effect. Because of that, the positive charge on the B carbon atom, that is going to be increased. Because of that, OH minus can attack it easily. So we'll generate respect to CO minus Na plus here, and the other carbon is going to be respectively reduced. That is CH2OH is going to be formed. Right? Very good. Look at this case, PH C double bond or C double bond H. Here what is going to happen? OH minus has to attack the particular carbon. Which carbon the OH minus is attacked? Like A and B. Among A and B, only B carbon is going to be attacked, because after that attack, then only we can lead to the formation of hydrogen loss. So we'll lead to the formation of PH C double bond O, CO minus COH CH. Negative charge and oxygen comes into CH bond leaves. You generate pH C double bond O. C double bond OH. Loss of hydrogen occurred. That hydrogen attack the carbon. C double bond O electron is moves away. pH CO minus CH. C double bond OH. O minus picks up the proton, forming pH CHOH. C double bond O minus Na plus. If you take NaOH, you get pH CH C double bond O minus. This is going to be the respective major product. Okay. If you take CCl3CHO, will it give Canizara or not?
Yes, sir.
CCl3CHO, will it give Canizara reaction or not? Canizara reaction, what is the condition?
No alpha hydrogen.
So alpha hydrogen should not be present. Is there an alpha hydrogen here?
No, sir.
So will it give Canizaro or it will not give?
Not give.
Why? CCl3CHO will not give Canizaro reaction. Even though it do not have alpha hydrogens. Reason is simple. Let us look at the reaction mechanism. CCl3CHO. CCl3CHO means C double bond H. Attacked by OH minus. OH minus acting as a nucleophile attack the electrophilic carbon. C double bond O pi electron and moves away. We generate CCl3CO minus COHCH. What is the rate determining step in Canizaro reaction?
Nucleophile.
Proton.
The rate determining step is loss of hydrogen, the transfer of hydrogen. So now if you look at this particular step, negative charge and oxygen comes into CH bond has to cleave. But the CCl3 minus is a very good leaving group or not? Yes or no? Here negative charge and oxygen comes into, instead of hydrogen loss, you will be having loss of CCl3 minus. You will generate a HC double bond OH plus CCl3 minus. Okay, CCl3 minus is a good leaving group. Is a good leaving group. Because of that, the hydrogen is not obtained. Because of that, hydrogen H minus ion isn't obtained. So Canizaro reaction do not occur. Even though CCl3CHO, even though in CCl3CHO we do not have alpha hydrogen, it will not undergo Canizaro reaction because CCl3 minus is a very good leaving group when compared to H minus. So respect to formic acid you will get and a CCl3 minus. CCl3 minus will be reacting with formic acid to form what? HC double bond O minus Na plus and CHCl3. This is a set of products obtained. This is a product set. Okay. So whenever we have a very good leaving group when compared to hydrogen, you should not be doing the Canizaro reaction. Like chloral will not be undergoing the respective Canizaro reaction. A next type of chemical reactions of aldehydes and ketones. In that category, you will have electrophilic substitution reaction. If you look at C double bond H, like benzene connected with C double bond H, C double bond H, like CHO group, benzaldehyde I have taken. CHO is electron withdrawing or electron donating group. CHO is it electron withdrawing or electron donating, students? C double bond O pi electron density is in resonance with the carbon pi electron density of benzene. It is electron withdrawing group. The pi electron density of benzene will be in resonance with the C double bond O pi electron density. Thereby electrons are moving away from the ring. Because of electron withdrawing nature, it will develop positive charge at ortho and para. Because of electron withdrawing nature, ortho and para positions will be getting the positive charge. Because of the positive charge at ortho and para, what you are going to have, the electrophilic substitution is not going to happen at ortho and para. Rather, meta position is electron rich when compared to ortho and para. So CHO is a meta directing group. And we all know that when we have electron withdrawing group, the electrophilic substitution reactions are going to be very less because electron density present inside the ring has been decreased. Yes or no? Aromatic aldehydes and ketones undergo electrophilic substitution at the ring, in which the carbonyl groups acts as deactivating and meta-directing. It is a deactivating group and meta-directing. So electrophilic substitution occurs at a meta position. So if you look at, take the benzaldehyde and do the nitration, you will be having meta-nitro benzaldehyde. Okay. So electrophilic substitution reactions will be undergoing at a lesser tendency because of deactivating group. Because CHO is a deactivating group, because it is withdrawing the electron density from the ring, thereby decreasing the electron density on the ring. Because of decreased electron density, these reactions, the electrophilic substitution reactions, are not going to be happening at a greater rate. So these are the different types of chemical reactions shown by carbonyl compounds. So then comes the next type of functional group, carboxylic acids. Carboxylic acids, if you take, they can be again classified into aliphatic as well as aromatic. In the aliphatic carboxylic acid, we have alkyl group connected to C double bond OH, whereas in the aromatic, we have some aromatic ring connected to C double bond OH. Aliphatic carboxylic acid means to the functional group C double bond OH, we have the aliphatic group connected. That means carbon-carbon chains, no rings. And aromatic means we have an aromatic phenyl rings connected. Acid derivatives, well, there are 4 types of acid derivatives which we are going to look carefully. Acid halides, acid anhydrides, esters as well as amides. There are 4 derivatives: acid halides, acid anhydrides, esters and amides. If you look at these derivatives, I have also given you the order, like which are more reactive towards nucleophilic addition elimination. Which are more reactive?
Acid halide is more reactive.
Acid halides, based on electrophilicity of the carbon, we have discussed, students. It is similar to nucleophilic substitution reactions. Like whenever you take an acid halide and do the reaction, it will be similar to nucleophilic substitution, but not SN1, SN2. Nucleophilic substitution by addition elimination type is going to happen. The addition elimination type. We will be looking at all the reactions. Let us start with the structure of carboxylic acid. In the carboxylic acid structure, we have C double bond group connected to OH. We can all say lone pair of electron present on oxygen. They were in resonance with the pi electron density of C double bond O. Because of they are in resonance, we will be having different resonating structures. So we can simply write lone pair of electron present on oxygen in resonance. So the positive charge on this particular carbon is nullified, and this oxygen have the positive charge now. So first one starts with the methods of preparation by the oxidation of alcohol. Alcohols, if I take a primary alcohol upon treatment with a strong oxidizing agent, we will be getting the respective carboxylic acid. But secondary alcohol treated with a strong oxidizing agent will get what? Secondary alcohol treated with a strong oxidizing agents will be getting ketones. Tertiary alcohol treated with a strong oxidizing agents, no reaction. Only with copper in the presence of high temperature, dehydration occurs. Primary alcohol, strong oxidizing agents, KMnO4H plus, KMnO4OH minus, K2Cr2O7, H2CrO4. All these are strong oxidizing agents. Strong oxidizing agents are KMnO4H plus, K2Cr2O7H plus, H2CrO4. That is CrO3 in the presence of water. Whenever we have chromic oxide in anhydrous medium, that will be acting as a milder oxidizing agent. Chromic oxide in the acidic medium or water medium, that will be acting as a strong oxidizing agent. We all know these are the strong oxidizing agents. Primary alcohol with a strong oxidizing agent itself undergo reduction, itself undergo loss of oxygen. So it will be giving oxygen to primary alcohol to form the respective carboxylic acids. Is that clear, students?
Yes, sir.
Yes.
Yes, right. Primary alcohol will be converted to respective carboxylic acid whenever you treat with strong oxidizing agents. But secondary alcohol will form ketones. And from alkyl benzene, if you look at this benzene group substituted with CH3, or carbon connected with carbon which have pi bond or oxygen or hydrogen linkage, in the presence of strong oxidizing agent, it will be converting into respective C double bond OH. This reaction we have seen even in the hydrocarbons as well. From alkyl benzene, the alkyl benzene or carbon which is having connection with the pi bonds or oxygen or hydrogen which is directly connected to the phenyl group, that upon treatment with the strong oxidizing agents, what are the strong oxidizing agents? Like these KMnO4H plus, K2Cr2O7H plus, KMnO4OH minus upon heating. Upon these oxidizing agents, this carbon which is having pi linkage or hydrogen linkage or oxygen linkage will be converted to respective carboxylic acid or carboxylates. This is obtained in acid medium. In acid medium, we will be getting carboxylic acid. In a basic medium, you will get. In a basic medium, you will be getting the respective carboxylates. Got this or not? In acid medium, you will be getting the respective carboxylic acid, whereas in the basic medium, you will get the respective carboxylate. Mechanism is not required. So you have methyl benzene, toluene, you treat with KMnO4 or K2Cr2O7 in the presence of H plus, or KMnO4OH minus upon heating gives respect to benzoic acid. Yes or no? What happens in this case?
No oxidation.
No oxidation because carbon is not connected to pi bonds or hydrogen or
Hydrogen.
oxygen. So it is connected with 3 methyl groups. So no oxidation. No oxidation because no hydrogen, no pi bond or no oxygen. This is happening in the presence of KMnO4H plus, you can say, or K2Cr2O7H plus. The first two reactions are like from the oxidation of primary alcohol. Second one is going to be from the alkyl benzenes, you will be getting respective benzoic acids or benzoates. The third one will be from nitriles and amides. From nitriles, if you do the acidic hydrolysis of nitriles, you will get respective carboxylic acid. If you do the basic hydrolysis, you will get what? In the basic hydrolysis, the carboxylates are obtained because whenever we have a basic medium, the OH bond is going to be cleaved. And how the mechanism you can understand? RC triple bond N, you are doing the acidic hydrolysis treated with H plus. Can I say lone pair of electron present on nitrogen that will be attacking the H plus? That will be attacking the H plus. So as soon as it attacks, what is going to happen? You get R C triple bond nitrogen. Nitrogen will now have a new bond with the hydrogen where nitrogen used its lone pair, so it will have a positive charge. This is now going to be attacked by water. Now what happened in the first step? RC triple bond N treatment with H plus. The electrophilicity of the carbon has been increased. The carbon triple bond nitrogen is there. Carbon is actually less electrophilic because the pi electron density movement is just because of electronegative difference. But now the lone pair of electrons and nitrogen attack the H plus, thereby nitrogen gets a positive charge, thereby the C triple bond pi electron density is moving towards the nitrogen greatly. So H2O is now going to be acting as a nucleophile and it can easily attack the more electrophilic carbon. As soon as this attack occurs, what happens? You will get RC. As soon as this attack occurs, the pi electron density moves towards nitrogen. So we get carbon double bond nitrogen. Nitrogen regains the lone pair. NH bond is as it is. Carbon forms a new bond with oxygen. Oxygen has two OH bonds, but oxygen used one of its lone pair. So oxygen only has one lone pair and a positive charge. The positively charged oxygen is not so stable, so it will attract the OH electron density. Lone pair of electrons and nitrogen picks up this proton. As soon as that occurs, what you will get? Alkyl group are connected to carbon, carbon double bond nitrogen. Nitrogen will form two NH bonds now, and it will be having a positive charge. And again, we have oxygen with a regained lone pair to two lone pairs, and you have one OH bond. And now we have one more H2O. H2O from the reaction mixture again acts as a nucleophile. It will again try to attack this electrophilic carbon. Why it will attack? Because the pi electron density of carbon and nitrogen, that is moving towards nitrogen. So lone pair of electrons on carbon attack, pi electron is moving away, generating what? Generating RC. Carbon is connected to one OH group. Carbon also connected to one more oxygen, where only one lone pair is there, two OH bonds and a positive charge. And nitrogen will have a regained lone pair and two NH bonds. Lone pair of electrons and nitrogen, they try to pick up this proton because oxygen bearing positive charge. So OH electron density moves away. It will lead to the formation of R, C, OH, C, OH, and nitrogen will have three NH bonds now, and it lost its lone pair, so positive charge. So lone pair of electrons and oxygen comes into, because ammonia is a good leaving group. Ultimately, we will have R, C double bond O, oxygen with only one lone pair, positive charge, one OH bond, and one OH group as well as, and ammonia is lost. The lost ammonia can easily pick up this proton, leading to the formation of R, C double bond O, OH plus NH4 plus ion. Okay, this is nothing but a carboxylic acid. And here lot of bonds are going to be broken. So in this reaction, you have to, these reactions you have to do at high temperature. So the bond cleavage is going to be easier. Acidic hydrolysis of cyanides will form carboxylic acid. Basic hydrolysis will be forming respective carboxylate. Basic hydrolysis is also similar. But if I do the basic hydrolysis, the OH minus will act as a nucleophile, because OH minus is a better nucleophile when compared to H2O. So OH minus, since it is a better nucleophile, there is no need to actually increase the electrophilicity. Why we are increasing the electrophilicity in the acidic hydrolysis? Because H2O is a poor nucleophile. If OH minus is there, that can directly go and attack the carbon, generating the movement of C triple bond pi electron density. Okay, so ultimately, if you do the basic hydrolysis, you get carboxylate, because the carboxylic acid also produced, that will undergo again loss of H plus ion, because base will pick up the proton. Acidic hydrolysis of nitrile form carboxylic acid, basic hydrolysis form carboxylates. Similarly, you can do the reaction with amides. pH C double bond NH2, acidic hydrolysis will form what? Same type of reaction. pH C double bond NH2. We are doing the acidic hydrolysis. So lone pair of electrons and oxygen, they will pick up the proton. As soon as they pick up, what happens? You will get R C double bond O. Oxygen only one lone pair, positive charge OH bond, and NH2 with one lone pair, and it is going to be attacked by H2O. Lone pair of electrons and oxygen attack the carbon, so you will generate pH C double bond O. Oxygen only one lone pair, but as soon as this attack occurs, the pi electron density moves away, right? So we have pH COH, oxygen two lone pairs, and NH2 as it is, lone pair of electrons and nitrogen, and oxygen one lone pair, two H bonds and a positive charge. OH electron density is moving towards oxygen, lone pair of electrons and nitrogen picks up this proton, ultimately leading to the formation of pH COH, COH NH3 plus. Lone pair of electrons and oxygen coming to, ammonia is lost, so get pH C double bond O, one lone pair, positive charge OH bond, OH, and NH3 plus is lost. It can pick up the proton to form pH C double bond OH and NH4 plus. Okay, so if you do the acidic hydrolysis, you will get respect to benzoic acid. If you do the basic hydrolysis, you will get the respect to benzoate. Is that clear, students?
Yes.
Right. From Grignard agent, from the Grignard agent also we can produce respect to carboxylic acid. How we can produce? Grignard agent will be acting as a base whenever we have acidic proton. Grignard agent will act as a nucleophile whenever there is no acidic proton. So Grignard agents will react with respect to carbon dioxide. Grignard agents react with carbon dioxide in the acidic medium to form respect to carboxylic acids. And the reaction will be in this manner. pH MgBr. pH MgBr means pH minus MgBr plus. pH minus MgBr plus, that will be reacting with carbon dioxide C double bond O, C double bond O. pH minus, because it is nucleophilic, it attacks the electrophilic carbon. The pi electron density moves away towards oxygen. So as soon as that reaction occurs, you get C. pH is connected to carbon, C double bond O, and carbon is also connected with oxygen with O minus, and it will develop electrostatic force of attraction with Mg Br plus. And now we are doing the acidification. You will generate pH C double bond OH, and this MgBr plus will pick up OH from the water to form MgBrOH. So respective benzoic acid is going to be obtained. This was the mechanistic approach. By the oxidation of primary alcohol, by the oxidation of alkyl benzene, by acidic hydrolysis or basic hydrolysis of nitriles or amides, and also from Grignard reagents, we can produce respective carboxylic acids. With the mechanism I am writing here, you can understand all the details as well. From acid halides and anhydrides, if you look at acid halide treatment with the H2O, anhydride also treated with H2O, directly you are getting respective CH3 C double bond OH group. That means OH is going to be substituting the chlorine. It is a nucleophilic substitution by addition elimination type. Nucleophilic substitution. It is a nucleophilic substitution by addition elimination type. And do we require water H plus here or not? Do we require acidic medium? Because in the acidic medium, the electrophilicity of the carbon is going to be increased. Do we require that or not? In the case of acid halides and acid anhydrides, acidic medium is not required. Direct hydrolysis is going to happen. Why? In case of acid halides and anhydrides, acidic medium is not required. Acidic medium is not required as they are more electrophilic. The carbon here is more electrophilic. The C double bond of carbon is going to be more electrophilic. You cannot argue like chlorine, lone pair of electrons of chlorine, they are in resonance. Why? Because for chlorine, inductive effect is dominant when compared to mesomeric effect. So chlorine on as a whole, it withdraws the electron density present in carbon chlorine bond, thereby increasing the positive charge. In anhydride also, lone pair of electron oxygen that can be in resonance, but oxygen is in resonance with the 2C double bond O, thereby decreasing the partial positive charge is less. Acid halides are more electrophilic than acid anhydrides. Because of that electrophilic nature, we don't need the acidification. So the whole point of doing the acidic hydrolysis is to increase the electrophilicity. That is not required because they are already more electrophilic. So H2O, even though it is a weak nucleophile, that will be getting attacked. That will be attacking the electrophilic carbon. Take CH3 C double bond O. I will be taking the anhydride O C double bond O CH3. Do the reaction with H2O. So lone pair of electron present on oxygen, they will be attacking the carbon. The C double bond of pi electron is to move away. We will generate what? CH3 C double bond O, oxygen connected to carbon, carbon connected to CO minus now, and the CCH3, it is connected to new oxygen. In the new oxygen, only one lone pair is there. Other lone pair is lost in the new bond, so positive charge and two OH bonds. Negative charge on oxygen comes into. As soon as negative charge comes into, the CO electron density is going to be lost, leaving out what? CH3 C double bond O minus acetate ion. Along with this acetate ion, you will generate CH3 C double bond O, oxygen with one lone pair and two OH bonds. Acetic acid is acid. Acetate ion is a base. Base will pick up this proton. OH electron density will be given to, generating CH3 C double bond OH plus CH3 C double bond OH. Yes or no? Ultimately, we have replaced this total group with OH or not. So nucleophilic substitution occurred. But what type? Addition, first added, then elimination. Okay?
Yes, sir.
Yes, right. From esters, we can do the esterification. If you remember esterification reaction, in the esterification reaction, there exists an equilibrium between the reactants as well as the products. What are the reactants? Acid plus alcohol will be reacting in acidic medium to form respective. Acid and alcohol in the acidic medium will be reacting to form respective ester and water. And there exists an equilibrium. So if you remove water from the reaction mixture as soon as it is formed, If you remove water from the reaction mixture as soon as it is formed, the reaction moves in the forward direction where more esters are going to be present. If you add water, if you add more amount of water, then the reaction proceeds in the backward direction. That means hydrolysis of esters occurs and you will be generating acid and alcohol back. Okay, esterification we'll again study like the same reaction, same esterification which we studied in alcohol, that we'll again study in the reactions of carboxylic acids, because carboxylic acid is a reaction of carboxylic acid which involve the cleavage of CO bond. But in alcohol, the OH bond is cleaved. Acidic hydrolysis of esters gives directly carboxylic acids, while if you do the basic hydrolysis, you will get carboxylate because base picks up the proton from the carboxylic acid. So if you are doing basic hydrolysis, you will get carboxylates. Again, you have to do the acidification to give respective acids. So ethyl benzoate, when you treat with H3O+, you will get benzoic acid and C2H5OH. Similarly, ethyl butanoate, you treat with NaOH, you will get a CH3, CH2, CH2, CO minus Na+. Carboxylate you will get. You do the acidification, you get the acids. And how is this reaction is going to happen? Let us take a ethyl benzoate, pH, C double bond O, C2H5. Let us do the acidic hydrolysis. First one is simple. Lone pair of electron present on oxygen. They are going to be attacking the H plus to increase the electrophilicity. Because in acidic hydrolysis, H2O is the nucleophile. H2O is not a great nucleophile. So you have to increase the electrophilicity. But in basic hydrolysis, OH minus is a nucleophile. OH minus is a good nucleophile. It can attack the less electrophilic carbon also. So what happens in the acidic hydrolysis? You have to increase the electrophilicity, pH C double bond O. Oxygen only one lone pair OH bond and a positive charge. Oxygen connected with C2H5. Now H2O acts as a nucleophile. So lone pair of electron on oxygen, they will be attacking the carbon. C double bond O pi electron density moves away. You generate pH. Carbon is now connected with oxygen. Oxygen regains the lone pair, two OH bonds, two lone pairs on oxygen and one OH bond. Carbon, oxygen, new bond. Oxygen only one lone pair, two OH bonds and a positive charge on oxygen. Carbon, oxygen bond as it is. And this oxygen is connected to C2H5. Lone pair of electron present on this oxygen that can pick up the proton. Why? Because oxygen possesses positive charge is unstable. OH electron density is moving. So we'll generate what? pH, COH, COH, and oxygen, only one lone pair, one OH bond and C2H5 and a positive charge. Lone pair of electrons on oxygen comes into CO electron density is given to oxygen, leading to the formation of pH, C double bond O, one lone pair positive charge OH bond, OH. Along with that, you will generate C2H5OH. This upon loss of H plus forms pH C double bond OH. The H plus whatever you are taking, that is released in the final step. So that means it is acid catalyzed. This reaction is just catalyzed by the acid. The acid is not required in the stoichiometric quantity, because after every reaction you are releasing back the H plus ion. And that H plus can be using the, that H plus will be used to increase the electrophilicity of the next ester, thereby continuing the reaction. And you get an alcohol. Acid and alcohol are obtained whenever you do the hydrolysis. That means adding more water to the ester in the acidic medium produces acid and alcohol. If you remove water from the reaction mixture, you will have more ester in the reaction mixture. Right, students? Then comes the next category. Carboxylic acids are higher boiling liquids. This is simple. Why? Because they have two hydrogen bonding sites. Because of their extensive intermolecular hydrogen bonding only, we are saying that carboxylic acids exist even in the vapor state, they exist in the dimer form. Because of that only, we will study the formality for carboxylic acids, not any other concentration term. Carboxylic acids are higher boiling liquids than aldehydes, ketones, and even alcohols of comparable molecular masses. This is due to more extensive association through intermolecular hydrogen bonding. Two hydrogen bonding sites are there. Partial negative developing attraction with partial positive, partial negative and partial positive. The hydrogen bonds are not broken completely even in vapor phase. In fact, most carboxylic acids exist as dimer. in the vapor phase or in aprotic solvent also. And they are going to be developing electrostatic force of attraction with water molecules also, that is hydrogen bonding with water. Because they are developing hydrogen bonding with water, they are even soluble in water. With increase in molecular mass, the solubility is going to be decreased because the hydrophobic chain is going to be increased. Hydrogen bonding of RC double bond OH with water. Boiling point, if you look at generally carboxylic acids greater, then alcohols, then ketones, then aldehydes, ethers and alkanes. This is a scenario for similar molecular mass based on intermolecular force of attraction. And you have to obviously compare for similar molecular mass species. You cannot compare alkane of a molecular mass 200 with the carboxylic acid of a molecular mass 60. That is wrong comparison, because with increase in molecular weight, van der Waals forces increases. With increase in van der Waals force of attraction, obviously the boiling points are going to be affected. Right, students? Is that clear so far?
Yes.
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 Yes, right. Then the formation of respective anhydrates, chemical reaction. If you look at formation of anhydrate means what? Anhydrate is species obtained by the loss of water. So RC double bond OH plus RC double bond OH upon H plus on heating, or P2O5 upon heating. P2O5 is a dehydrating agent. It will form respective anhydrate. Anhydrate is obtained by the loss of water. How is that loss of water is going to happen? The same reaction, if you think, like for amide also, RC double bond NH2 P2O5. What is going to happen? Loss of water will happen. Loss of water will occur in such a way such that you will be generating respective nitrile. RC triple bond N and H2O is going to be lost. Let us look at the mechanism to understand the details. RC double bond OH, RC double bond OH, treated with H plus ion. Lone pair of electron present on oxygen, they will be attacking the H plus. As soon as they attack, you can generate RC double bond O, oxygen only one lone pair, positive charge, OH bond, and OH will be as it is. We have one more molecule of carboxylic acid, RC double bond OH. Yes or no? This RC double bond OH, lone pair of electron present on this oxygen, that will be acting as a nucleophile now. It will attack the electrophilic carbon. And why the acidic condition is required? Why the acidic condition is required? If you do not take the acidic condition, the other molecule of carboxylic acid will not act as a nucleophile. Why? Because carboxylic acid is a poor nucleophile. Why? Because the lone pair of electron on oxygen, I am attacking this particular carbon, but we all know that lone pair of electrons on oxygen, they were in resonance also. Yes or no? So since it is a poor nucleophile, we have to increase the electrophilicity. As we increase the electrophilicity, this reaction is going to happen. We have R group connected to C double bond O, C double bond O connected to oxygen. Oxygen has only one lone pair. The other lone pair involved in the new bond formation. In the new bond, you will be having what? In the new bond, you will be having carbon connected with a CO, C double. Oxygen will regain its lone pair, two OH bonds. Here also we have one OH group. Yes or no? This carbon also contained one OH group. And this carbon contains the alkyl group R. Now, can I easily say lone pair of electrons present on this oxygen on the OH, they can pick up the proton. Why? Because OH electron density is moving towards oxygen. As soon as they pick up the proton, you will be regaining the lone pair on this oxygen atom, generating what? RC double bond O. Oxygen regains its lone pair connected to carbon, carbon connected to one OH group and alkyl group, as well as oxygen will now have two OH bonds and a positive charge. H2O is a good leaving group, so lone pair of electrons of this oxygen comes into. As soon as they come into, loss of water occurs. So loss of water occurs, and we will write the product here. R group, alkyl group connected to C double bond O. Oxygen one lone pair or two lone pairs. Carbon C double bond O, only one lone pair and a positive charge and OH bond connected to alkyl group. This will undergo loss of H plus ion to form respective R C double bond O, O C double bond O R. The H plus ion which is used in the first step, that is again regained back in the last step. So we can just do the we can just take the acid in the catalytic amount, not the stoichiometric amount, and we have to do the reaction at a higher temperature so that the bonds are going to be cleaved easily. Okay, simply you can write, you cleave the CO bond in one carboxylic acid and OH bond in other carboxylic acid. Loss of water occurred. We generate the respective anhydride or C double bond O, C double bond R. And this was a mechanistic approach. Same amide also will undergo dehydration in the presence of P2O5. P2O5 is a very strong dehydrating agent. It will remove the water from the amide, forming nitriles. Carboxylic acid undergo dehydration to form anhydrides. Amides will undergo dehydration to form nitriles. I can do the acidic hydrolysis of nitriles to form carboxylic acids back. Okay. Like from the amide, I can generate nitrile by doing the dehydration by treating with P2O5 in heating. The nitrile I can do acidic hydrolysis to produce respective carboxylic acids. Like that, one functional group to the other functional group, I can do the conversion. First reaction is formation of anhydride. Next, esterification reaction. The same mechanistic approach. Carboxylic acid react with alcohols of phenols. Carboxylic acid react with alcohols of phenols in the presence of acid, concentrated H2SO4 or dry HCl to form esters. This is called as Fischer esterification, and there exists an equilibrium. As I was discussing, there always exists an equilibrium. Which bond is cleaved in acid, students?
CO bond.
Acid will undergo cleavage of CO bond. Alcohol will undergo cleavage of
OH bond.
OH bond. Very good. R C double bond OH, R dash OH will form R C double bond OR dash plus H2O. CH3 C double bond OH plus CH3 OH. This CO bond, OH bond is cleaved. You'll generate CH3 C double bond OCH3. CH3 C double bond OCH3. Mechanism is the same mechanism. First, a lone pair of electrons on oxygen attack the H plus, increasing the electrophilicity. Then alcohol acts as a nucleophile, attacks. Okay, final same mechanism. CO bond will be cleaved in acid. Alcohol OH bond is going to be cleaved. So you have what type of species? In the alcohol OH bond is cleaved. In the acid CO bond is cleaved. You get C6H5 C double bond O18 CH3. Along with that, water is there. If we remove water from the reaction mixture, we get more ester. Mechanism is simple. First step, lone pair of electrons on oxygen attack the H plus. Why? We have to increase the electrophilicity. Why? Because alcohol is a poor nucleophile. So now alcohol attack the carbon, C double bond pi electron and stay attacks. That moves away. This carbon is sp2 hybridized, but now it becomes sp3. Yes or no? So tetrahedral intermediate will be getting. Now proton transfer will occur. Why? OH electron density is moving towards oxygen. So lone pair of electrons on oxygen, they can pick up the H plus, OH2 plus. Loss of water occurs. In the loss of water, lone pair of electrons on oxygen comes into generate R C double bond O plus OH OR dash. Ultimately, loss of H plus occurs. You will generate ester. From the protonate ester, you will generate back the ester. This was the mechanistic approach. And I have already given the conditions whenever I give the salicylic acid. Like if you go with the examples, like salicylic acid, I am treating with alcohol. Which group will react? Salicylic acid. Alcohol or phenol in H plus medium, you have to think of esterification reaction. Salicylic acid reacts with alcohol or phenol in the acidic medium, will be undergoing the respective esterification reaction. That means the COOH group will be reacting with the alcohol or phenol. But if you treat this with same salicylic acid, if you treat this with acetyl chloride or acetic anhydride, like acid halide or anhydride, what happens?
OH reacts.
Okay, O acylation occurs. OH is going to be reacting O acylation is going to happen. CH3 C double bond O Cl ROH. What is going to happen here? Same type of reaction. Nucleophilic substitution by addition elimination type. CH3 C double bond O Cl plus ROH. CH3 C double bond O Cl has more electrophilic carbon, so the nucleophile, poor nucleophile can also attack. 5 electron and moves away, generating CH3 CO minus CCl. Oxygen with only one lone pair, positive charge, H and R group. Negative charge on oxygen comes into chloride ion is lost. Loss of chloride ion. CH3 C double bond O. Oxygen one lone pair, OH bond and OR bond and a positive charge. The chloride ion will try to pick up this proton, forming CH3 C double bond O, OR plus a HCl. So this is going to be formed in the first case. Whenever you take PHOH instead of OR, you will get OPH. This is a mechanism. Okay. Acid halide reacting with alcohol or phenol will form respective esters. Same type of reaction, you will be generating what? CH3 C double bond O, CH3 C double bond O, OR or CH3 C double bond O, CH3 C double bond O, OR and CH3 C double bond O, OPH. Earlier we form HCl, right? But now the leaving group is acetate ion. The acetate ion will pick up the proton to form acetic acid. CH3 C double bond OR plus acetic acid or CH3 C double bond OH, OPH plus acetic acid. These are the set of products obtained. Is that clear, students?
Yes.
Yes.
Right.
Yes.
And esterification, if you look at the rate, esterification reaction, the alcohol is going to attack the electrophilic carbon if the alcohol is bulky group. If in the alcohol bulky groups are there, alcohol cannot act as a good nucleophile because of steric repulsions. If the bulky groups are present in carboxylic acid also, then also during steric repulsions, the reaction is not going to happen. So rate of esterification is inversely proportional to steric hindrance. This is the point. Rate of esterification is inversely proportional to steric hindrance. So reactivity of alcohol, which alcohol will be more reactive?
Primary.
Primary, because in the tertiary alcohol we have bulky groups. Reactivity of acids, again primary acids, like
Primary
bulky groups are more in the tertiary. Like if COH is connected to carbon, which is tertiary carbon, in that case due to steric repulsions, the nucleophilic attack is not going to happen. So this is the order for the rate of reactivity. Rate of reactivity of rate of esterification or rate of reactivity of compounds towards esterification is inversely proportional to steric hindrance. Greater the steric repulsions, lesser will be the rate. As I was telling, salicylic acid you are reacting with CH3OH and H plus, PHOH and H plus. Salicylic acid treated with a alcohol or phenol in acidic medium, you have to think of which reaction? Esterification.
Esterification.
Yeah, esterification means which groups are going to be affected, Fatima?
COH.
COH will be affected, CO bond is cleaved, OCH3 is going to be substituted. Here OH bond is cleaved, here CO bond is cleaved. In the PHOH, OH bond is again cleaved. We get generate C double bond OPH and OH. The first compound is said to be oil of wintergreen, methyl salicylate. The second compound is salol phenyl salicylate, which also has antiseptic properties. Salicylic acid treated with a methyl alcohol or phenol will be undergoing the respective esterification to form respective esters methyl salicylate or phenyl salicylate. Like esterification reaction occurs. Esterification occurred. Reaction with PCl3, PCl5 and SOCl2, same type of reactions whatever you are going to have. I'll write the mechanism here. For one compound I'll write. So RC double bond OH, RC double bond OH plus PCl5, PCl3, PCl5, SOCl2, they are going to be acting as respective electrophiles, and respective carboxylic acid is going to be acting as a Carboxylic acid will be acting as a nucleophile. So what is going to happen in the first stage? What is going to happen in the first stage, students?
The lone pair will attack phosphorus.
Lone pair of electrons present on oxygen, they are going to be attacking the phosphorus, but which lone pair? Although we have lone pair of electrons on this oxygen, they were in resonance with the C double bond O. This lone pair is actually attacking. Because
ठीक है बात सुन बात जा बाहर जा आप सीरियस सच्ची में मैंने कॉल कर देते मैं कर दी बात
RC double bond OH treating with respect to PCl3, PCl5, SOCl2. If you consider PCl5 reaction, phosphorus connected to 5 chlorines. Lone pair of electron present on this oxygen, they are going to be attacking the phosphorus because that will be a good leaving group. It will lead to the formation of RC double bond O. Oxygen only one lone pair positive charge. As soon as this attack occurs, the chloride is lost. We have OH bond. Phosphorus will now have 4 chlorines. Loss of chloride occurs. The chloride which is lost, that is now going to attack the electrophilic carbon. It won't pick up the proton. The chloride which is lost, that will try to attack the electrophilic carbon. C double bond of pi electron and moves away. You generate RCO minus CCl. Oxygen with one lone pair OH bond and a positive charge. Oxygen connected to phosphorus, which has 4 phosphorus chlorine bonds. Negative charge on oxygen now comes into this carbon oxygen bond is going to be cleaved because it will lead to the formation of phosphorus oxygen bond. So that will ultimately form what? RC double bond of Cl plus phosphorus OH bond and phosphorus connected with 4 chlorines. Negative charge or lone pair of electrons on oxygen that will be coming into to form a P double bond O. So that will lead to the formation of what? P double bond O, and as soon as it comes into, chloride is lost. Negative charge, lone pair of electrons on oxygen, only one present, positive charge OH bond, 3 phosphorus chlorine bonds, and whatever the chloride is lost, that will try to pick up the proton to form P double bond O, PCl, PCl plus HCl. You are getting the same or not? RC double bond OH plus PCl5 gives RC double bond of Cl. It is a nucleophilic substitution, but what kind? Addition elimination type. Okay. Nucleophilic substitution only occurred, but addition elimination type. Like carboxylic acid treated with the PCl3 forms RC double bond of Cl plus H3PO3. 3 moles react. Carboxylic acid react with PCl5 to form acyl halide RC double bond of Cl plus POCl3 plus HCl. It can also be reacting with a thionyl chloride. Carboxylic acid react with thionyl chloride to form respective acid halide, and SO2 and HCl are going to be eliminated. SO2 and HCl, they are going to be gases, so they can be removed from the reaction mixture easily. So this is going to be the easiest way to prepare the respective acid halide as well. The third way. Similar to that of alcohols reacting with PCl5, PCl3, SOCl2, carboxylic acids also react with PCl3, PCl5, SOCl2 to form respective acid halides. Is that reaction clear, students?
Yes, sir.
That's right. Reaction with ammonia. Whenever you try to treat with ammonia, simple reaction is acid-base reaction occurs. So lone pair of electron present on nitrogen, they will pick up the proton. OH electron instead is given to oxygen. You will be forming respective salts. Ammonium carboxylate is going to be formed. That is RC double bond O minus NH4 plus. RC double bond O minus NH4 plus ammonium carboxylate will be formed. If you try to heat this, rearrangements will occur leading to the formation of amide. Mechanism not required. Heating this will form RC double bond O NH2 and H2O is lost. Simple ammonia means without heating you will form the respective salt, ammonium carboxylates. But heating that will form amides. Carboxylic acid treated with ammonia will form respective salts of carboxylate ion, like ammonium carboxylate is obtained. That upon heating, it undergo rearrangements and loss of water will happen. Acetic acid plus NH3 will give what? Ammonium acetate, NH4 plus CH3, CH3 C double bond O minus NH4 plus. This ammonium acetate upon heating will form CH3 C double bond NH2, ethanamide, and what is lost? CH3 C double bond NH2 plus what is lost? That is acetamide is going to be obtained. Benzoic acid upon heating and like benzoic acid, C double bond OH upon heating with ammonia, it will form respective C6H5 C double bond O minus NH4 plus. If you try to heat it, you will generate C6H5 C double bond NH2. Respective amide is going to be formed. C6H5 C double bond NH2, that is going to be formed. This is a reaction with ammonia where you are converting the respective carboxylic acid to respective amides. Phthalic acid, if you treat with ammonia, what you are going to expect? Here you will get O minus NH4 plus, O minus NH4 plus. Ammonium phthalate, you will get salt. If you try to heat this salt, you will get what? C double bond NH2, C double bond NH2. Phthalamide you will get or not? Because C double bond O minus NH4, loss of 2 mole of H2O, it will lead to the formation of respective C double bond O minus NH4 plus will be converted to C double bond NH2. C double bond O minus NH4 plus, that will also convert to C double bond NH2. Phthalamide is obtained. Now, if you try to heat the phthalamide strongly, what will happen? If you try to heat the phthalamide strongly, you will lose the ammonia, leading to the formation of respective phthalimide. You know imide phthalimide, right? Which process? Gabriel phthalimide you are going to use?
Yes, sir. Yes,
Gabriel,
sir.
using Gabriel phthalimide, can I prepare aromatic amines?
Yes, sir.
Yes or no, Nandana?
Sir, what was the question, sir?
Using Gabriel phthalimide synthesis, can I prepare aromatic amides, aromatic amines? Gabriel phthalimide synthesis is useful. We can only prepare aliphatic, not aromatic. Why it is so, that we'll study in the next chapter, that is nitrogen and its compounds. Okay. Because what actually happens is, first in the Gabriel phthalimide synthesis, we have alcoholic OH which picks up the proton, you get N minus. That will be treated with alkyl halide. So you'll have N group connected to alkyl group, where in the alkyl halide the carbon halogen bond is going to be cleaved. If you take aromatic like a haloarine, then the carbon halogen bond cannot be cleaved because it exhibits partial double bond character. So there, whatever the phthalimide you are using, that is obtained in this manner from the phthalic acid. And how this phthalimide to phthalimide can happen? Phthalimide is C double bond O NH2, C double bond O NH2 on the two adjacent carbon atoms. So can I say lone pair of electron present on nitrogen that will be attacking this particular carbon, C double bond O pi electron and moves away? That can happen. If that happens, you will have CO minus, CNH2, carbon nitrogen new bond, two NH bonds present, and you have C double bond O. And nitrogen will have a positive charge because it clots its lone pair. We have one more NH2, right? So this NH2 can easily pick up this proton, so that NH electron density can be given to nitrogen, forming what? C double bond O, CO minus, right? CO minus, CNH3 with a positive charge on nitrogen, connected with NH. NH regains the nitrogen regains the lone pair, C double bond O. Negative charge on oxygen comes into ammonia is lost. C double bond O NH, C double bond NH plus ammonia. This is how phthalimide to phthalimide can be obtained. This was the mechanistic approach. And from the phthalimide, you can prepare primary amines. Primary aliphatic amines can be obtained by Gabriel phthalimide synthesis. Phthalimide treated with alcoholic OH followed by alkyl halide upon heating will generate, and lastly acidic hydrolysis you have to do. That will form primary aliphatic amines. Right, students? This was a reaction with ammonia. Then the reduction of carboxylic acids will be done in the presence of LiLH4 or not? Is LiLH4 can LiLH4 reduce carboxylic acids?
Yes, sir.
Yes, sir.
LiLH4 can reduce all polar functional groups which are containing polar pi bonds. NaBH4 can only reduce aldehyde,
Four
ketone,
groups.
acid halide, and imine. What are those four? Aldehyde, ketone, acid halide, and imine. H2 in the presence of metal catalyst can reduce all polar and non-polar except carboxylic acid.
Carboxylic acids.
So for reduction, H2 in the presence of metal catalyst is not going to done. We can be using LiLH4 or you can also use B2H6. Diborane. Carboxylic acids are reduced to primary alcohol because oxygen containing functional groups will be converted to respective primary alcohols by lithium aluminum hydride or better with diborane. Diborane is also a better reducing agent. Diborane does not easily reduce functional groups such as ester, nitro, halo. Sodium borohydride does not reduce the carboxyl group. So diborane is going to be best group to convert the respective carboxylic acids to primary alcohol. And we all know that mechanism is not going to be discussed because that is out of our standard, out of your 12th standard. So we can easily understand with the help of diborane, what we are going to have is carboxylic acid groups can be reduced. Like if I have groups like this, NO2, C double bond OH, C double bond OR, and I am treating with B2H6, or I am treating with some compound X, which is forming the product in this manner. NO2, C double bond O, C double bond OH, acid is converted to CH2OH, C double bond OR. What is X? X is LiLH4, NaBH4, H2 in the presence of palladium, B2H6. Such type of questions. If you look at the conversion, nitro group is not changed, ester is not changed, only carboxylic acid has been affected or not. Diborane does not easily reduce functional groups like ester, nitro, halo. Sodium borohydride does not reduce carboxyl group. So only C double bond OH is affected. So it is not LiLH4. It can't be NaBH4. It can't be H2 in the presence of palladium. So it has to be B2H6. Such type of questions like which is the reducing agent used in the above conversions can be expected. So be careful with that. Which reducing agents can convert what type of functional groups and all. Next, decarboxylation reaction. What was the mechanism or what was the intermediate?
Carbanion.
Carbanion. We have discussed in alkanes also. And if it is a beta keto acid, what was the intermediate? 6-member transition state.
6-member transition state.
Like very good. So removal of CO2 from carboxylic acid is known as decarboxylation. Removal of carbon dioxide from carboxylic acid is said to be decarboxylation. And reagents used are NaOH and CaO. That is nothing but soda lime. CH3COH. If you look at the mechanistic approach, CH3C double bond OH treated with OH minus base. Base picks up the proton, forms CH3C double bond O minus. The C minus will come into carbon-carbon bond. Electron density will be given to CH3. CH3 minus and CO2. CH3 minus will have electrostatic force of attraction with Na plus. Yes or no? And we have CO2. CO2 is also affected with a OH minus. That will lead to the formation of OH, C, O minus, C double bond O. Because CO2 will have this type of structure. How is carbon removed whenever you are treating with soda lime? This OH bond is there, right? The CH3 minus will be reacting with a C, O minus, C double bond O, COH, CH3 minus will pick up this proton, OH electron instead is given to oxygen, generating CH4 plus C double bond O minus, O minus. That means the carbon dioxide is removed in the form of CO3 2 minus ion. The carbon from the respective carboxylic acid is removed in the form of CO3 2 minus, that is Na2CO3 is going to be formed. Rate of decarboxylation is directly proportional to stability of carbon ion, and this was the mechanistic approach. But if you do the decarboxylation of beta keto acids, there the carbon is removed in the form of just carbon dioxide, not CO3 2 minus, because there the reaction mechanism proceeds through 6-member transition state. And if you want to compare the rate of decarboxylation, you have to just look at the stabilities of carbon ions. Right, students, let us look at some examples. Write the order of rate of decarboxylation for following compounds. In the compound you get CH3 CH2 minus. In the compound B you will get CH2 double bond CH minus. In the compound C you will get CH triple bond C minus. Which carbon is more stable? C, then B, then A, because negative charge on more electronegative, because it is sp hybridized. Sp hybridized carbon possessing the negative charge, more electronegative atom possessing negative charge is more stable. So CBA, that is the rate of decarboxylation for the respective carboxylic acids given to you. CBA. Write the order of rate of decarboxylation for the following compounds. C6H5CH2COH, pH CH2 C double bond OH. This compound B is CH3 C double bond O, CH2 C double bond OH. Here what type of carbon you will get? Is it beta keto acid or not? Compound
Yes,
B.
sir.
So whenever you have beta keto acid, that will be undergoing the decarboxylation just by heating. You don't need to check the carbanions and all. So obviously beta keto acid will be, for beta keto acids undergo decarboxylation by simple heating. Not only beta keto acids, beta gamma unsaturated compounds will undergo decarboxylation by simple heating also. Similarly, beta gamma, like let us take an example instead of writing the statement, like CH3 CH double bond CH, CH2 C double bond OH. This is alpha beta gamma. Beta gamma unsaturated, if you try to write the example, if you try to heat it, what you are going to get? You will have CH3 CH double bond CH, CH2 C double bond O, OH. This carbon pi electron density will moving further. This OH electron density moving inside. This electron density moving inside. You will get the transition state in this manner. CH3 CH, a new bond is going to be formed. The old bond is going to be broken. A new bond is supposed to be formed here. This bond is supposed to be broken. This bond is supposed to be broken. And these bonds are as it is. This is the 6-member transition state. This will immediately lead to the formation of what? CH3, CH will form a new bond CH2, and this CH double bond CH is there, right? That is going to be forming now. That will be forming what, students? Single bond CH. That will form double bond CH2, and ultimately CO2 is eliminated. Look at the positions now. I am giving isotopes. This alpha carbon is 13, C13, C14, C15, C13, C14, C15. Like C12, C13, C14 are the isotopes, right? C12, C13, C14. This is C12, this is C13, this is C14. 6-member transition state C12, C13, C14. Earlier double bond was between 13 and 14. Now the double bond is between 12, 13, 14. So double bond has been shifted. Okay. Beta gamma beta gamma unsaturated acids undergoes decarboxylation by simple heating, similar to beta keto acids. Everyone got this or not? Similar to beta keto acids, beta gamma unsaturated acids will undergo decarboxylation by simple heating. This is the transition stage, but in this process, overall you are going to have the alkene formed, hydrocarbon formed, but the unsaturation of the hydrocarbon that has been shifted. The double bond position has been shifted. These are products. Right?
Yes,
Chemical yes. The next reaction we can think of is HVZ reaction, Hell-Wolfhard-Zelinsky reaction. What happens in HVZ reaction?
chlorine is added to alpha. It is alpha carbon.
Yes, very good. So how is the mechanism going to be? Look at the part. Carboxylic acids having alpha hydrogen atom are halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus to give alpha halocarboxylic acid. How is this going to happen? First, let us take RCH2 C double bond OH. RCH2 C double bond OH. I am treating with a red phosphorus in the presence of X2. So P plus X2, can I say PX3 is formed? That means what is going to happen? Phosphorus halide reacting with carboxylic acid. You will get what? Acyl chloride or not? RCH2 C double bond X is going to be obtained. Whenever you do the reaction of RCH2 C double bond OH treated with a PCl3 or PCl5, you get what? Like let us do the reaction with P plus Cl2 only. P plus Cl2 means you will get a acyl chloride. P plus Cl2 means you get carbon chlorine. Can I write the respective tautomer? RCH2 C double bond O, Cl is obtained. If you try to write the like keto form and the enol form, in the enol form I can write as RCH double bond COH and CCl. This enol form will be reacting with Cl2 again. The lone pair of electrons on oxygen, they will come into the pi electron instead attacking from the alpha position. You will get what? Cl2. You will get R, CH is connected with Cl. Carbon, carbon, single bond now. C double bond O, oxygen will have only one lone pair and a positive charge and OH bond, and also carbon is connected with chlorine. The chlorine which is present here, and here the chlorine, as soon as the pi electron instead attacks chlorine, the carbon chlorine bond is the chlorine chlorine bond is going to be lost. So we have one more chlorine atom which is lost as chloride ion. That chloride ion which is lost, that will pick up this proton, ultimately forming RCHCl, C double bond O, oxygen regain its lone pair, and we have Cl. This is nothing but acyl halide. Acyl halide, we are doing the hydrolysis. Hydrolysis of acyl halides do not require any acidic condition because this carbon is more electrophilic in nature. So what is going to happen? So H2O, being a nucleophile that can attack the carbon easily, pi electron density moves away, generate RCH, CCl, CO minus, carbon connected to oxygen, only one lone pair. One lone pair and two OH bonds. So we'll write a carbon chlorine here. Carbon only one lone pair, positive charge and two OH bonds. Chloride is a good leaving group. Negative charge on oxygen comes into carbon chlorine bond leaves. You will generate what? RCHCl, C double bond O. Loss of chloride occurred. Oxygen contained only one lone pair, positive charge, two OH bonds. The Cl minus will try to pick up this proton, generating RCHCl, C double bond OH plus HCl. Yes or no? So ultimately what you can say, we have to look at the reagents, whatever you are using. RCH2 C double bond OH, red phosphorus in the presence of halogen, that is the first set of reagents. Second is the hydrolysis. On the alpha position, halogen is going to be substituted. First step is forming the respective acyl halide, then tautomerase structure, then doing the attack with Cl2. Then again attack of H2O, because H2O is a nucleophile. Even though it is a poor nucleophile, the acyl halide carbon is more electrophilic, forming the acid back and HCl is obtained. And if you treat this with further, like P and Cl2 further, then whatever the alpha carbons you are going to have, on the alpha positions, how many hydrogens are there? All of them are going to be subsequently replaced with halogens. Replaced with the halogen. Like if you treat this again with the phosphorus in the presence of Cl2, the other CH bond that is also going to be replaced, substituted. CH3, CCl2, CCl, CCl, C double bond OH is obtained. CCl, CCl, C double bond OH is going to be obtained. Is that clear, students?
Yes.
Yes. Very good. And this was a very good method. Why it is a good method? Why HVZ reaction has importance? Because on the alpha carbon we have substituted halogen, means the carbon chlorine bond can be replaced by carbon cyanide bond or not. Like CN group can be replaced if I treat with KCN. Let us look at this equation, then proceed further. What happens in the first case? Phosphorus in the presence of Cl2 gives A. Like PCl3 will form CH3, CH2, C double bond Cl. Yes or no? CH3, CH2, C double bond O. Here you have to give hydrolysis, they have to mention. If they have not mentioned, that is not going to be a correct question. Yes or no? CH3, CH2, C double bond OH, PCl2 means we can stop the reaction at respect to acid halide. CH3, CH2, C double bond Cl. Mentioned hydrolysis means you have to do the respective HVZ reaction. We will form CH3, CHCl, C double bond OH. Look at the options. Based on the option, choose the right option, right one. Because if in all the options, if they are given alpha substitution, beta substitution and all, then you have to do HVZ only. If acid halides are given, then you have to go with the acid halide only. Now this has been treated with alcoholic OH. Alcoholic OH is a strong base, undergoes elimination. Beta elimination, this is alpha carbon, this is a beta carbon. So you get what? Like we have CH2H, CHCl, E2 elimination is going to happen, C double bond OH. So OH, this proton can also be picked up. Elimination can also occur. OH minus can pick up this proton, CH electron and comes into CCl leaves. You get CH2 double bond CH, C double bond O minus K plus. With respect to this particular carbon chlorine bond, E2 elimination occurred. With respect to the C double bond OH, alcoholic OH behaves as a base. So what happened? If you look at the first compound A, you treat compound A with KCN, students. K plus Cn minus, you will get what? CH3. Like you treat compound A with a KCN. You treat with KCN. You will get CH3, CHCN, C double bond OH. You treat this with H plus in the presence of H2O upon heating. You have a cyanide. Acidic hydrolysis of cyanides will give what? CH3CH, C double bond OH, C double bond OH. So we have produced dicarboxylic acids or not? 1,3-dicarboxylic acids can be prepared by the treatment of respective alpha halo substituted carboxylic acid with the KCN followed by acidic hydrolysis. Okay, so it can actually provide a path to actually include a nucleophile at the alpha position. HVZ reaction provides a path to include any nucleophile at the alpha positions. Right. Then the next type of reaction of carboxylic acid, ring substitution. So ring substitution, again carboxylic acid is a good electron withdrawing group. Since it is electron withdrawing group, it will decrease the electron density inside the ring. So when compared to ortho and para, meta is going to be electron rich, because ortho and para will have positive charge, meta will be neutral. So among carboxylic acids, like aromatic carboxylic acids undergo electrophilic substitution reactions in which the carboxylic acid will act as a deactivating and meta directing. because it is withdrawing the electron density. They, however, do not undergo Friedel-Crafts reaction. Why? Because the carboxyl group is deactivating and the catalyst aluminum chloride gets bonded to the carboxylic acid. What is the role of catalyst? AlCl3 has to produce the respective electrophile, but here the carboxyl group itself react. So when you do the nitration, benzoic acid concentrated HNO3 H2SO4, NO2 plus is the electrophile and substitute the meta position. When you do the halogenation, what is going to happen? Br plus is going to be obtained, which is going to be substituted meta position. So meta bromo benzoic acid is obtained. Friedel-Crafts reactions not happen. Why? Because the carboxylic acid will react with the, like the carboxyl group will itself react with the respective AlCl3 to form some complex, and AlCl3 is not used to generate an electrophile. And these are all deactivating groups. That is why they do not undergo electrophilic substitution at a greater rate. Whenever we have electron donating group, they will be obviously having great rate toward the electrophilic substitution reaction when compared to electron withdrawing groups. And the next type of reaction, dry distillation of calcium salt of carboxylic acid we can take. If you take the dry distillation of calcium salt of carboxylic acid, what happens in this case? RC double bond OH treated with CaOH second phase upon heating produces RC double bond R plus CaCO3. How is this happened? Like RC double bond OH plus CaOH second phase, right? RC double bond O minus RC double bond O minus will develop electrostatic force of attraction with Ca plus 2, and this Ca plus 2 will undergo the loss of CaCO3. This is nothing but your CaOH taken twice reacting with 2 moles of carboxylic acid forming RC double bond O minus, RC double bond O minus, developing electrostatic force of attraction with Ca plus 2. When you heat this, you will form, this is going to be lost, that is loss of CaCO3 occurs, and alkyl group are connected with carbon, that is C double bond O, and one more alkyl group. You will generate respective ketones. This is also a method of preparation of ketones. Like if you take acetic acid, CH3 C double bond OH 2 mole treated with a CaOH taken twice upon heating forms a CH3 C double bond O CH3. Along with that, CaCO3 is obtained. Is that clear, students? And this proceeds through ionic intermediates because Ca plus 2 will develop electrostatic force of attraction with RC double bond O minus ions. Because Ca plus 2 produces respect to OH minus picks up the proton. Two acids have taken, two OH minus ions picks up 2 protons to form 2 carboxylate ions and Ca plus 2. That upon heating will undergo loss of CaCO3. That upon heating will undergo loss of the respective CaCO3. Next comes the heating effect of carboxylic acids. This is what we are discussing. First one is beta keto carboxylic acids. Beta keto carboxylic acids, whenever you try to heat, what is going to happen? Beta keto and beta gamma. Beta keto and beta gamma, unsaturated carboxylic acids, they'll undergo decarboxylation just by heating, and it will lead to the formation of respective alkanes or derivatives of alkane. Like in the beta keto acid, you have this type of intermediate. See, like transient state, if you write CH3CO forming a new bond with oxygen, this OH bond is going to be cleaved. We have CH2, new bond is formed. Okay, this is a transition state. It will immediately lead to the formation of CH3, COH, double bond CH2 plus CO2. This is a enol form, forms a respective keto form, tautomere, CH3, C double bond O, CH3. That means ultimately the CH2 is connected with hydrogen and carbon dioxide is lost. The CH2 is connected with the hydrogen, that's it. And CO2 is lost as the decarboxylation happened with the loss of CO2. In the presence of soda lime, for normal carboxylic acids, the decarboxylation occurred with the release of CO3 2 minus. So here what happened? You get CH3, C double bond O, CH2H. Acetone is obtained. What is going to happen? This is the alpha carbon, this beta carbon. On this alpha carbon, beta keto acid, this alpha carbon is going to pick up the hydrogen. So we form respective cyclohexanone and CO2 is released. And you are going to release CO2. Same, this is your alpha carbon, beta carbon. This is the alpha, this is beta. So these are all beta keto acids only. So alpha carbon pick up the proton here. This alpha carbon pick up the proton. So you get same cyclohexanone, but 2 moles of CO2 is going to be released. Similarly, beta, gamma, unsaturated acids undergoes decarboxylation by simple heating. Is that clear, students?
Yes.
Yes, sir.
Yes, right. Dicarboxylic acids. I have given one shortcut to you. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. 1, 2, 1, 3 dicarboxylic acid will undergo decarboxylation. Like upon heating 1, 2, 1, 3 acids, loss of what happens? Loss of, earlier also we have discussed this. If I have 1, 2 acid, like oxalic acid is a 1, 2 dicarboxylic acid. Malonic acid is a
Water.
Malonic acid is a 1, 3 dicarboxylic acid. Loss of CO2 occurs for 1, 2, 1, 3. For 1, 4, 1, 5, you will have anhydride formation, loss of water occurs. For 1, 6, 1, 7, you will be having loss of CO2 and water. And you can have anhydride formation. The anhydrides, whatever they are going to be formed, they will be only of 5-membered and 6-membered. You will never form, we can never form 7-membered anhydrates or 4-membered anhydrates or 3-membered anhydrates. This rule is nothing but, what is this rule? Planck's rule. Planck's rule says 5-membered and 6-membered anhydrates are stable and they can be formed and not the heavier ones. 5, 6-membered anhydrides can be formed as they are stable, and not the heavier ones or lower ones. So dicarboxylic acid, let us take COH, oxalic acid. I have given one shortcut. Like OMA is such good apples. In the oxalic acid, you have direct 2 COH connected. Malonic acid, between 2 COH, there will be one CH2 group. Oxalic acid, malonic acid, succinic acid, glutamic acid, and glutaric acid and adipic acid. So in the oxalic acid, you don't have any CH2. So upon heating, what will happen? Upon heating oxalic acid, what you are going to get? Loss of CO2. CO2 is going to be lost. You will have hydrogen directly connected. HC double bond OH plus CO2 is obtained. It is 1, 2 acids. Malonic acid, 1, 2, 3. 1, 3 dicarboxylic acids. What happens? CO2 is going to be lost. You will have CH3, COH, acetic acid and CO2. And how it is lost? There was a transition state. How is that going to be lost? Although we are saying CO2 is lost, that is lost in this manner. Okay, you should know how to write the product first. Mechanism is a different. scenario. First, learn how to write the product. OH electron density comes into CC electron density is given to carbon. This carbon picks up the proton, forming CH, C double bond OH. Along with this, CO2 is obtained. Okay. This is directly hydrogen, right? Hydrogen connected to carbon. H, C double bond OH plus CO2. Same here. CH2, C double bond OH, C double bond OH. OH electron density is given. The CC electron density picks up the proton, forming CH3, C double bond OH. Along with that, CO2 is obtained. So 1,2,1,3 acids will lead to the formation of carboxylic acids, and carbon dioxide is eliminated. Can I discuss this 1,4, 1,5, 1,6, 1,7 also?
Yes, sir.
Yes, sir.
Just wait few more minutes. So it is what acid? 1, 2, 3, 4. 1, 4 acid. It will undergo what, students? Loss of
Water loss.
Water.
What is lost? And you will get anhydride. Blank's rule is going to be followed. So you get CH2, CH2, C double bond O, C double bond O, succinic anhydride is obtained along with loss of water. Glutaric acid, nothing but 1, 2, 3, 4, 5, 1, 5 acid. Again, loss of water will happen. You will generate a 6-membered anhydride, that is a glutaric anhydride. Anhydrides are named from the respective acids from which they have been produced. So O minus such good apples, that is a shortcut. Succinic acid and glutaric acid, that is 1, 4 and 1, 5 acids. And how the mechanism you can think of? CH2, CH2, C double bond OH, C double bond OH. And you are heating this in the presence of, you are heating this. So lone pair of electrons and oxygen, they attack the carbon. C double bond electron density moves away. You get CH2, CH2, CO minus, COH, carbon oxygen, one lone pair, positive charge OH bond connected with C double bond O. So this OH will pick up this proton, leading to the formation of CH2, CO minus, OH2 plus. Oxygen regain its lone pair, CH2, C double bond O. Ultimately, negative charge comes into, loss of water occurs, leading to the formation of succinic anhydride. Same thalamide we produce, right? In the similar manner, you form the respective succinic anhydride. 1, 4, 1, 5 acids will undergo loss of water. 1, 2, 1, 3 will undergo loss of carbon dioxide. If you go with 1, 6, 1, 7 adipic acid, 1, 2, 3, 4, 5, 6. You cannot remove loss of water because you get a 7-membered anhydride which is unstable. And pimalic acid, that is also, you cannot remove the loss of water. Both the carbon dioxide you have to remove and water also you have to remove. Ultimately, you have to connect this carbon with this carbon, you get a ketones, cyclic ketones. Carbon dioxide and water, both CO2 and H2 are lost. You get a CH2 minus is going to be attacking this particular carbon, loss of water occurs. Whenever you do with a 6-membered, CO2 is lost, H2O is lost. This carbon is going to be connecting with the sixth carbon, CH2, 5 carbons and 6 more carbon, and you have loss of CO2 and H2. Adipic acid and pimalic acid, that is 1, 6 and 1, 7 acids, they will be heating. If they are heated, you will undergo loss of carbon dioxide as well as water, and you will generate cyclic ketones. Cyclic ketones obtained. 1, 2, 1, 3 gives carboxylic acid, 1, 4, 1, 5 gives anhydrates, 1, 6, 1, 7 gives cyclic ketones. And in the 1, 2, 1, 3, CO2 is lost, 1, 4, 1, 5, H2O is lost, 1, 6, 1, 7, both CO2 and H2 are lost. These are the heating effects of respective carboxylic acids. Right, students, let us stop the discussion here. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.